Hello, class. We want to welcome you back. Today, we want to look at chapter 4. We are treating chapter 4 today. And in chapter 4, we are going to study chemical quantities and aqueous reactions. We'll study chemical quantities and aqueous reactions. So chemical quantities in chemical reaction are studied under the class called reaction stoichiometry. So let's consider this reaction. The equation is balanced. So this is a balanced chemical reaction. Let's consider the reaction. In this chemical equation, the coefficient in a balanced equation, this chemical equation, they are there to specify the amount of moles of each of the substances involved in the reaction. So what are coefficients? So 2 is a coefficient for CH18. 25 is the coefficient, it represents the number of moles of oxygen in this reaction. 16 is a coefficient, it represents the number of moles of carbon dioxide in this reaction that is produced. And 18 is a coefficient, it represents the number of moles of water molecule that is produced. So according to this balance equation, when we look at it, the information we can get is that 2 moles of C8H18 is reacting with 25 moles of oxygen to produce 16 moles of carbon dioxide and 18 moles of water. This numerical relationship between quantities in a chemical reaction is what we call stoichiometry. So when we talk about stoichiometry, we are talking about this kind of numerical relationship between quantities in chemical reactions. Predicting amounts from stoichiometry. The amount of any other substance in a chemical reaction can be determined from the amount of just one substance in the chemical reaction. So, for example, we can find the amount of carbon dioxide that can be made from 22 moles of C8H18 in this reaction. This reaction below here is a combustion reaction. So from this reaction, we know that 2 moles of C8H18 produces 16 moles of carbon dioxide. We'll use that as conversion factor. So to get the amount of carbon dioxide from 32 moles of C8H18, we are going to use this relationship that we get from the balance equation as a conversion factor, and this is what happened. So it means when we use 22 moles of C8H18, we are going to get 176 moles of carbon dioxide using this relationship mole ratio. We call this a mole ratio, which we got from the balance equation as conversion factor. We can also, so this is practice. You can practice this. How many moles of water are made in the combustion of 0.10 moles of glucose? So this is glucose, and this is water. So it shows that 1 mole of C6H12O6 produces 6 moles of H2O. So our mole ratio is 1 mole of C6H12O6 over 6 mole of H2O, or 6 moles of H2O over 1 mole of C6H12O6. So we have to use our mole ratio as conversion factor. So this is the mole ratio. We have come up with 2 conversion factors. So if we want to find how many moles of water are produced in the combustion of 0.1 moles of glucose, we can just put 0.10 moles of 6H12O6 times 6 moles. We will use this conversion factor, O6. So we want to cancel moles of glucose. Then we are going to multiply 0.1 by 6. So we are going to have 0.6 moles of H2O. So please make sure you practice and practice and practice. So this is another example. Estimate the mass of carbon dioxide produced in 2026 by combustion of 3.5 times 10 to the 15 grams of gasoline. Assuming that your gasoline is octane, that's the molar mass of octane. This is octane. So this is the balance equation. And our question is to estimate the mass of carbon dioxide that is produced. So the relationship, the balance equation for the reaction gives the mole relationship, and we need it as conversion factor. It gives the mole relationship between the amount of C8H18 and that of carbon dioxide. But we need to know the mass relationship. So we are going to come up with a conceptual plan. So we have to move from the mass of octane to moles of octane, then the moles of carbon dioxide and mass of carbon dioxide. Here the molar mass is used as conversion factor. Here the mole ratio this is from the balance equation. Then here is the molar mass that we'll use as conversion factor. So those are the conversion factors that we are going to use. So let's continue. So in that problem, what is given? The mass of octane is given, but we have to find the mass of carbon dioxide. So this is our plan. We are going to move from mass of octane to moles of octane to moles of carbon dioxide to grams of carbon dioxide. And these are what we are going to use as conversion factors. So our solution. So that's the conversion factor from here the molar mass of octane. This is the conversion factor from the balance equation. This is the mole ratio. And this is the conversion factor molar mass of carbon dioxide. So we arrange it. This is the mass of octane, convert it to number of moles of octane, convert it to moles of carbon dioxide, then convert it to mass of carbon dioxide. So we are going to have 1.1 times 10 to the 16 grams of carbon dioxide. Now we want to look at limiting reagent, theoretical yield, and actual yield. We are going to use making pizza so that we can have an understanding of what this is all about. So consider that the recipe for pizza is 1 crust plus 5 ounces of tomato sauce plus 2 cups of cheese. This will give us our pizza. We are going to relate our recipe as a balance equation. So the question is, what will happen if we use 4 crusts, 15 ounces of tomato sauce, and 10 cups of cheese? How many pizza are we going to get? That's the question. So this is our recipe. This is our recipe. In chemistry, we can say it's our balance equation. And this is the reagents. I mean, the reagents that we have, reagents. That we want to use. We want to find out how much quantity of the substance we're going to have. But before we do that, we have to calculate what we are going to expect before we go to the lab and do the reaction. So, of course, this is the recipe. This is what we have. So, in order to do this, we are going to use what we have to find out how much pizza each of these reagents that we have, these substances that we have, will give us. That's what we'll do first. So 4 crusts, we are going to expect to have 4 pizza if the quantity that we have is 4 crusts. We have 15 ounces of tomato sauce. From 15 ounces of tomato sauce, we expect to have 3 pizza. We have 10 cups of cheese. From 10 cups of cheese, we are using our conversion factors for mole ratio to show us how much pizza we're going to have from this recipe. So from 10 cheese, we are going to expect to have 5 pizza. This is what we are expecting. But the difference is that all these substances have to work together to give us a pizza. So how many pizza are we going to have? We're expecting to have using this reagent that we have. So in summary, this is maximum number of pizza we can make from each ingredient. Each ingredient could potentially make a different number of pizza, but all the ingredients have to work together. All of them have to work together. We have only enough tomato sauce to make 3 pizza. So once we make 3 pizza, the tomato sauce runs out. No matter how much of the other reagents we have, we cannot make any other pizza because all the ingredients need to work together. So we can make only 3 pizzas. So the tomato sauce limits the amount of pizza we can make. In chemical reaction, we call this the limiting reactant or limiting reagent. The maximum number of pizza we can make depends on these reagents. And this maximum amount of pizza we can make, we call it the theoretical yield in chemistry. Excess reagent. So in our pizza mixture, 4 crusts, 15 ounces of tomato sauce, and 10 cups of cheese, we can only produce 3 pizzas. How many crusts are required to make 3 pizzas? From the equation, 1 crust makes 1 pizza, therefore 3 pizzas can be made from 3 crusts. So our pizza mixture has 4 crusts, meaning we have more than we need. So in other words, crust is in excess. Therefore, we will not be completely used. So excess reagents are not completely used. So reactants not completely used, consumed are called excess reagents. That's how we call them. Now let's apply this knowledge to chemistry. So we have a balance equation of CH4 plus 2 moles of oxygen to produce carbon dioxide and water. We can see it in the picture here. The equation for the combustion of methane implies that every 1 molecule of methane reacts with 2 molecules of oxygen. So that is our balance equation. That is our recipe. If we have 3 molecules of methane and 8 molecules of oxygen, which of these reagents, which of these reactants, methane and oxygen, will be the limiting reactant? So which is the limiting reactant? Let's find out. So we are going to use the 5 molecules of methane. Then we use the mole ratio and find out how much product are we going to have. You can use any of this. You can use carbon dioxide or use water. We just want to find out which reagent is going to produce more product or less product. So in this case, 5 molecules of methane, this is from the balance equation, it's a mole ratio. So we notice that we are going to have 5 molecules of carbon dioxide. Then now we take 8 molecules of oxygen. This is a mole ratio. We notice that 8 molecules of oxygen is going to produce 4 molecules of carbon dioxide. Since less carbon dioxide can be made from oxygen than methane, the oxygen is therefore the limiting reagent. Let's take another example. How many moles of silicon nitride can be made from 1.2 moles of silicon and 1 mole of nitrogen in the chemical reaction? This is the chemical reaction. This is the balanced chemical reaction. So what is given? We have 1.2 moles of silicon and 1 mole of nitrogen. And we want, this is the number of moles of silicon we are searching. I mean, trisilicon tetranitride. That's what we are searching. So our plan is to move from moles of silicon to moles of trisilicon tetranitride, then from moles of nitrogen to moles of trisilicon tetranitride. That which gives us the least amount of moles is the limiting reactant. So these are the mole ratios. For the different reactants and the product. So solution. So we get conversion factors from those mole ratios. So we notice that 1.2 moles of silicon will give us 0.40 moles of trisilicon tetranitride. And 1 mole of nitrogen will give us 0.5 moles of trisilicon tetranitride. So from this, you will notice that the silicon is giving us least amount of the product. So this silicon is the limiting reagent. So limiting reagent, silicon, is the limiting reagent. So let's go back to making pizza. So from our 15 ounces sauce, the number of pizza we can obtain is 3. So this is our theoretical yield. But let's assume now that as we are making the pizza, we burnt a pizza or some other uncontrollable event happened so that we could make only 2 pizza instead of 3. So that is what we actually got, even though we were expecting 3. So the actual amount of pizza made is called the actual yield. So the amount of pizza we were expecting to have made was called the theoretical yield. So our percent yield, how do we determine our efficiency, which we call the percent yield, is the actual yield over the theoretical yield times 100. That will give us our percent yield. That will give us our efficiency. So in this case, our efficiency is 67%. So theoretical yield and actual yield. So the theoretical yield will always be the least possible amount of product, and the theoretical yield will always come from the limiting reagent. Because both controllable and uncontrollable factors, the actual yield of the product will always be less than the theoretical yield. So the actual yield will always be less than the theoretical yield. Let's try another example. When 28.6 kilograms of carbon are allowed to react with 88.2 kilograms of tin 4 oxide in the reaction below, 42.8 kilograms of titanium is titanium 4 oxide, not tin, titanium 4 oxide. So I'll go back again. When 28.6 kilograms of carbon are allowed to react with 88.2 kilograms of titanium oxide in the reaction below, 42.8 kilograms of titanium are obtained. Find the limiting reactant, theoretical yield, and the percent yield. So this is the equation below. This is the equation that we want to use. So that is the equation. We saw the equation. So what is given? The given quantity is 28.6 kilograms of carbon, 88.2 kilograms of titanium 4 oxide, and 42.8 kilograms was the product. That's what we actually got. So we want the limiting reactant. So we need a plan. So from the kilogram, the masses of the reagent carbon and titanium 4 oxide, we are going to convert it to grams so that we can be able to find the number of moles. So from there, we'll convert to the number of moles of carbon and titanium 4 oxide. Then now we'll convert to the number of moles of titanium, because that's what we want. We'll use the different reagents to find the number of moles that each can produce. The one that gives us the least amount of moles of titanium is the limiting reagent. So this is what the relationship that we need as conversion factors. So we know that 1,000 grams equals to 1 kilogram. The molar mass of titanium 4 oxide is 79.87 grams per mole. The molar mass of titanium is 47.87 grams per mole. The molar mass of carbon is 12.01 grams per mole. And 1 mole of titanium 4 oxide produces 1 mole of titanium. We got this from the chemical equation. And 2 moles of carbon will produce 1 mole of titanium, which is also obtained from the chemical equation. We are going to use all this as conversion factor. So our plan, we are going to find the number of titanium, the moles of titanium from the reagent carbon. And when you do that, this is it. We use all our conversion factors, and we got 1.19097 times 10 to the 3 moles of titanium from 28.6 kilograms of carbon. From 88.2 kilograms of titanium 4 oxide, we got 1.1043 times 10 to the 3 moles of titanium. So this amount is smaller than this. Which shows that titanium 4 oxide is our limiting reactant, and the theoretical yield is 1.1043 times 10 to the 3 moles of titanium. So theoretical yield is the product obtained from limiting reactant. That is what we are expecting. So the smallest mole of titanium was obtained from titanium 4 oxide. So our theoretical yield, we convert the moles to grams of titanium to kilograms of titanium. So this is our theoretical yield. Now we want to find the percent yield. It's actual yield over theoretical yield times 100. They gave us the actual yield to be 42.8 kilograms. So 42.8 kilograms of titanium over 52.9 kilograms of titanium times 100. So our percent yield is 80.9%. So thank you. We'll continue next class to solutions. So continue with solutions.